Swayam Prabha. Digital India. Educated India.
Hello, everyone. Welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Kanpur. We are well into our fifth week, and we have been looking at rather interesting notions on how to prove convergence of parameter identification systems. Right? Uh, we are, of course, motivated by these very nice background images that come up behind us. And this one is on a spacecraft which is orbiting the Earth. And we hope that the algorithms that we design and the algorithms that we are analyzing help us to develop autonomy for systems such as these. So, without delaying further, let's sort of look at what we were doing until the last session. Right. So, we moved on to trying to prove exponential stability of a standard parameter identification system. So this system 7.1 that you see here is actually very standard in parameter update laws. Yeah. So parameter update laws and the derivatives typically look something like this in a lot of applications, right? So we are trying to use persistence of excitation of this signal phi in order to conclude that you have in fact uh, stable parameter convergence, that is parameters converge to the true values if you have some persistently exciting signal and so on. All right, so in order to do that, we of course took a Lyapunov candidate, a valid Lyapunov candidate, and then we computed a v dot which we found was only negative semi-definite. But since we are interested in using this alternate exponential stability theorem, we are not too worried. Right? So we actually take the integral of this v dot, and this is what is this expression. So I'm going to highlight this again so that we can come back to this later. Right. Yeah, so we're going to come back to this later. So our subsequent attempts, like I said, are where to try to get a bound on this one. How did we begin? We started from the connecting the persistence of phi to UCO of this system. Right? So we showed that this system is in fact UCO because of the persistence of phi itself. All right. So this is where we were. Yeah. So we want to, of course, start from here. And so let me mark this. This is lecture 5.5. Yeah. So great. So now that we have established UCO of a particular system, we want to use the idea of UCO being invariant under output injection in order to get to our original system. Yeah, that's really the idea here. Okay. So what do we do for that? We consider a rather interesting output injection term, right? Which is basically this k of t is minus alpha phi of t, right? So of course this is a vector. It is a vector of dimension n. Therefore this k, the gain itself, is also a vector of dimension n. Yeah, right. Great. So then if we compute, so one of the requirements for the output injection theorem was we had to compute a moving average bound. Suppose we do that. So, and that is what it is, basically integral from t to t plus cap t of this quantity. And I remember that we do have some kind of persistence bound on this quantity. There is an upper bound on this quantity, and that's what we seek to use. it is well known that we use a rather well known equality, which is that non or phi transpose phi for any vector for that matter is the same as trace of phi transpose. And this, of course, is norm of phi squared. Correct. This is a very standard equality. Right? So here we have a norm of phi square because the alpha square can anyway be pulled out. It's just a scalar quantity. Right? And the norm of phi square can be written as the trace of phi transpose. Right? Why do we do that? Because we have an outer product here and we want to see an outer product here. That's it. Yeah, so trace is just the sum of the diagonal elements. Alright. So now if you look at this guy, you know that this is upper bounded by mu to I. So the trace of this, right, is upper bounded by mu2 times n. Right. So why? Because again we use the fact that trace of mu2 times the identity matrix is just n mu2. Yeah, because this is an identity matrix of dimension n. Yeah. So if you just sum mu2 on all the diagonals, you just get n times mu2. And that's what we get here, alpha squared n times mu. Alright. So now that we have a nice upper bound on this sort of the output gain, yeah, we know that A plus KCC is also UCO, right? So in this case, um, in this case, basically K is just the K of T, the small k of T, and C is basically just uh, phi transpose of T. Yeah. So if I substitute, right? So what do I get? A was 0, of course, right? Just from here, A is 0, C is phi transpose, and K is minus alpha phi. So if I just substitute here, just from our output injection result, which says that if you have a nice moving average bounded K, then you cannot destroy the UCO property if you do this output injection on the dynamics, then essentially what we get is A plus KCC is UCO. And if I just substitute all these quantities in here, I will just get that minus alpha phi transpose comma phi transpose is in fact UCO. Okay. So what do? So we go back to our this nice integral. Right? I'm going to make this smaller so we can see both. We go back to this integral in equation 7.3, and that's what is rewritten here. Yeah, it's rewritten in the entire form. Right here, it's just written as a phi transpose x whole square, but here we expand it. Right? That's all. And not just expand it. What else do? We write x in terms of the state transition matrices. Right. So which is what this is. I've written x as phi st xt. Right. So x's is phi st times xt. This is basically standard way of computing solutions for linear time varying systems using state transition matrices. Right. So if you want the solution at S, you take the state transition matrix from S to T and then multiply it by the value at xt. Now the important thing to remember is that, and I do that on both sides, of course, right? So the important thing to remember is that these two quantities are now independent of the integration variable, and therefore I can move them outside the integration. That's what we do. And what you're left with inside is again our favorite UCO granule. Yeah. So this is what we like. We want to see the UCO Grammy everywhere. Right? Why? Because we are proving some kind of UCO condition and we're going to leverage it to bound this thing. Yeah. So remember, so this is what we have for our expression here, right, with the UCO Grammy. And I also have that this system is now uniformly, completely observable, yeah, which was obtained by where output injection, right, through a nice game. Yeah, great. Now, what is this system? So that's what we want to do. We want to write this system out Yeah, what is this dynamical system? This dynamical system is just this and this, and because this is the A, this is the new C. This is the new A matrix, this is the new C matrix. And it's not the old AC, but this is the new A and new C matrix. And so this is the dynamical system, and this is the output matrix. And what do I have? I have a system which looks like this. I have a system which looks like this. Now, notice what is this system? This is in fact the system that we are trying to prove exponential stability of, right? So this system is exactly this guy, the same system. All right, it's exactly the same system. Okay, and this is an output. This output is, of course, you can see that this is not a real measurement. Yeah, I mean, I don't think anybody would be able to claim that if I used a sensor, I would measure something exactly like this. Yeah. So this is not like a sensor measurement. This is sort of an artificially created output so that you can complete your stability proof. That's it. Yeah, because we need an output injection. All right. That's all the purpose of using this Y. Yeah, this Y is not necessarily a real measurement from a sensor. So let's not sort of, befuddle ourselves and try to think that this is possibly some real measurement. It's not. I don't promise that it's any kind of a real measurement whatsoever. All I would say is it's just a construction for the purpose of analyzing stability here. Yeah, so the only thing we need to focus on is sort of this system. And that's good because this system is matching the system for which we want to prove stability. Now, what is the UCO Gramian corresponding to this? I know that this system is already UCO, yeah, with constants beta 1 bar and beta 2 bar. So what is the UCO Gramian for this? The UCO Gramian is T to T plus cap T, uh, P transpose S tau, sorry, P transpose ST, C transpose, which is phi S, C, which is phi transpose S, and the state transition matrix again, the DS. Yeah. So now let's look at this. And here the phi is corresponding to this system. Okay, the phi corresponds to this system. Yeah, the phi is the state transition matrix of this system. Right? Now, if you look at this carefully, this expression. Right? So what do I anyway? Before we do that, we know from the UCO criteria that this is less than equal to some beta 1 bar identity, and this is less than equal to so beta 2 bar identity. And so I have a bound on both sides, yeah, because of the UCO condition. Now, if you look at the Gramian expression here, you see that it is exactly identical to here. Yeah, it is exactly the same. Yeah, because phi here is the state transition matrix corresponding to the original dynamics, which is this. And so is this. This phi is also the state transition matrix corresponding to the same dynamics. Right? And the matrix in the middle, phi transpose, is of course the same. Yeah. So now the fact that these two are exactly identical helps us to bound this guy. Because of the UCO condition, I have a lower bound on this. Right? And because there's a negative sign, that is what we need. We need the lower bound. So what do we have? We use this lower bound to actually upper bound V dot as minus 2 alpha beta 1 bar norm xt squared. So there's no numbering in this. So to earlier Gramian, I would say. Or maybe I will just number it in sort of 7.35. Let me call this equation 7.35. This is 7.35. All right. So great. So I have an upper bound on the integral of v dot Yeah, and this is exactly of the form that we require in an alternate exponential stability theorem, right? And so, great. I have, in fact, proved that the equilibrium x equal to 0 for this sort of parameter identifier system is, in fact, exponentially stable, right? And this, of course, we have leveraged persistence of excitation, UCO, and UCO under output injection to do all this. Yeah. So, and as I had mentioned before, the y that we actually see is purely for analysis purposes. Yeah, there is no role of y, or there is no real measurement which can possibly resemble y. All right. So it's purely for the purpose of analysis. So yeah, just think of it as an artificial construction. Yeah. Now, there are also extensions of these, which is again something which appears very commonly in model reference adaptive control parameter identifiers, right? And that is this. This is not a time invariant system, so this is linear time varying system. Yeah. If you look at this linear time varying system, which is again something that is very common in model reference adaptive control. Error here is basically some kind of a tracking error, or because it's a model reference system. So E is the error with the model reference typically. So that's what is mentioned here. Is that called the no? Yeah. So tracking error E, and then you have a parameter estimation error theta tilde. Yeah, and usually this is the dynamics that you find. You will find like a uh, sort of an interesting dynamics where you have an A is basically the coming from the original system itself, no problem. Uh, B times phi is basically the dependence on the parameter. Yeah, because there's a parameter error that is, and it's an unknown parameter, so there is no way I can cancel the parameter term. So I sort of do the best, and so I get something in the parameter error, and I get something in the update law, which is depending on the E, on the tracking error. Yeah, so this is very standard in model reference adaptive control. When we get to that stage, you will see that our system turns out to be of this form. Okay. Now, further, if we consider, so therefore we are considering this linear time varying system, right? Um, Further, if we have AB to be a controllable pair, very standard assumption, and AC to be an observable pair, again a standard assumption. Further, if there exists uh, for a given positive definite symmetric Q, there exists a positive definite symmetric P such that this Lyapunov equation is satisfied and this PB equal to C transpose if both of these happen. And phi is absolutely continuous in phi dot. Right? Then you have that the origin of this system is uniformly globally exponentially stable if and only if phi is persistently excited. Okay, so this a lot of different points here. So these two I would say are like standard assumptions in linear systems. Standard assumption in linear observer and control. So nothing special about this. This is very standard assumption in linear systems observer and control design. So it's not like there's something uh, too new that we are sort of introducing here. The next condition here is like a exactly like a Lyapunov equation corresponding to AB Hurwitz. Yeah. So if your A matrix is a Hurwitz matrix, yeah, that's a stable matrix, then this sort of an equation is always satisfied. Yeah. If A is a stable matrix, a Hurwitz matrix, which is usually the case here, yeah, then this sort of an Lyapunov equation can always be satisfied. This is the sort of converse stability theorem for linear systems. All right. Yeah, converse Lyapunov theorem for linear systems. Now this condition is basically like a standard, what I would call a matching condition. So this is sort of additional. This is a matching condition. And of course, this we have not really defined what absolute continuity is. So I would ask you to look up the definition. Yeah, but the purpose of being absolutely continuous is just so that persistence, excitation, etc. are well defined. Yeah, because in order to do persistent excitation, you need to take an integral and so on and so forth. So essentially, we require phi to be absolutely continuous, and we also require phi and its derivative to be bounded. Okay. So this is a very, again, like a more I would call a regularity assumption, so that things are well defined. That's all. Yeah. So that things are well defined. All right. So then if we have these four conditions, like I would say relatively reasonable conditions. Yeah. Then you can actually claim that z equal to zero, that is the zero equilibrium, is in fact uniformly globally exponentially stable if and only if phi is persistently excited. So this, you can see, is an extension of the previous result. The nice cool thing here is that um, you when you say z is basically both these states together. You are saying not only do the tracking errors converge, but the parameters also converge. Yeah. So this is not very common in adaptive control. Yeah, let me be honest. In a lot of cases, when we solve adaptive control problems, you would, and we will do that very soon, you will start to see that parameter convergence is not usually guaranteed in adaptive. Yeah. All an adaptive control theorist will tell you is that uh, in the presence of an uncertainty, by designing a parameter estimator, what we can guarantee is that your tracking error, that is your control objective, which is, say, for example, your robot wants to move in some kind of a sinusoidal shape. Yeah. So basically, this kind of a tracking objective will be precisely met, no problem, even with the parameter uncertainty. But identification of the set parameter may not happen. Yeah. And that is where there is this requirement of persistence of excitation and so on. And also here too, the theorems that you have, right? The conditions that you have, or the theorems that you have, are rather limited in terms of uh, you know what kind of systems they can handle. Because if you notice, the two results that we saw are in fact only for linear systems. Yeah. It is not really that easy to come up with such conditions when your dynamics is nonlinear. All right. And that's what we are usually dealing with. We're usually dealing with nonlinear systems. Yeah. So uh, there is still a lot of open problems in trying to talk about parameter convergence for nonlinear systems. Yeah. So adaptive identification of parameters, that is precise identification of parameters, is not guaranteed in adaptive control. Yeah. There are only these few cases where in fact you have some results which typically work under persistence of excitation, and they guarantee that your parameters will also converge to the true value, right? On top of tracking errors going to zero. So tracking errors going to zero is guaranteed by all adaptive control, and that's what most practitioners are interested in anyway. Yeah, they don't care about really identifying and noting down parameters. Sure, but in some cases, yes, you are also interested in doing that, because once you identify the parameters precisely enough, and if they stay fixed, you can implement simpler controllers subsequently, and would not need to implement adaptive controllers. Yeah, so this is sort of what um, you know uh, is the conundrum in adaptive control. Of course, yeah, it provides a nice solution, but it also leaves something out there open to work. Yeah, great. So one of the other points, the final points on this additional result, is that this condition 3 that you have, that is this sort of condition, it it actually helps you to uh, ensure that this Lyapunov function works. Okay, and it's not very difficult to verify. I mean, we can actually take a very nice simple derivative here. So v dot from here becomes E transpose uh, P with E transpose P E dot. So this is, I believe, a constant P variable, right? Because A is absolute. A is a constant matrix. So we have, yeah, you will have, well, I'm going to write it out. E transpose P E dot plus E dot transpose P E plus theta tilde transpose theta tilde dot. Okay. And this, if I substitute for E dot from this guy here, right? So what will I get? I get E transpose P AE plus B phi transpose theta tilde plus same thing E transpose A transpose plus theta tilde transpose phi B transpose times PE plus theta tilde transpose, and theta tilde dot is just minus phi C. So minus theta tilde transpose phi times C. As usual, I have sort of gotten rid of all the time arguments, right? So if you look at just these two together, this becomes E transpose PA plus A transpose PE. Yeah, and then I'm left with uh, right, right. Then I'm left with uh, plus uh, twice. In fact, I'm just going to combine them. Theta tilde transpose uh, phi B transpose PE. I missed an E here, right? So I don't think we should have an half here, and so there should be a minus twice here, and so this is minus twice theta tilde transpose phi times C times E, right? So this, of course, is nice minus E transpose QE from our Lyapunov equation, and these two in fact cancel out, right? How? This is by virtue of the fact that uh, we have this set of a condition PB equal to C transpose. So if you see this PB equal to C transpose, so C is equal to B transpose. So these two are the same, so they actually cancel. So we are left with this kind of a minus E transpose QE, and this is our usual starting point. If you remember, right, this is where uh, you have V dot is negative semi-definite, and you start to integrate V dot, and you go on with the proof. So we are not completing the proof for this case. Yeah, you can look up the proof. This work is by Narendra sometime in 1977-78, I believe. Yeah, so you can look up the proof if you wish, but this is the starting point. You remember, we have a negative semi-definite V dot. We start to integrate the V dot, start to use P, UCO, and all such conditions on phi, and then we sort of try to go on from there. So I would strongly recommend that you try to see how you can complete this. Great. So what did we look at today? We completed the proof for parameter identifier convergence under persistence of excitation. we saw how we could leverage the PE, UCO under output injection, this alternate exponential stability theorem. So basically, all the neat little results that we looked at from the beginning of this week, we could leverage that to actually prove that you have this parameter identifier convergence. Right? We also saw an extension of it, right, where you have this sort of a system which contains the tracking error E from the model reference adaptive control setting, which you will look at in the future, and also the theta tilde. So you had both the E dynamics and the theta tilde, that is the parameter error dynamics, and we claimed that uh, theta and E tilde are exponentially, uniformly, globally exponentially stable at 0 if this, again, this phi type of a gain term is phi t is in fact persistently excited. Right? And we saw what kind of conditions are required for that. Right? So anyway, we'll continue more on this vein. I mean, try to wrap up this sort of material in the next session. And yeah, that should be an interesting discussion. All right. Thank you, folks.